We have some good articles available on the topic, yet it is one of the poorly understood concepts. Ethereum community at large lacks an understanding of how the block gas limit is chosen, what factors must be considered when setting it, and what is the optimum level. With this talk, our goal is to share information on the concept and explain the reason why it is the way it is. To describe the notion, we are joined by none other than Vitalik Buterin, the co-founder, researcher of Ethereum blockchain. Thank you for joining us, Vitalik.
Thank you, Burja. It's good to be here. Good to be back at the lovely PEEPanEIP. Also, definitely excited to see Ethereum turning 6 today. We've definitely come a long way as a community since those early days when half the entire Ethereum team got together and was able to fit in a single room in Berlin when we were actually seeing the blockchain launch for the first time. So, we've made a huge amount of progress, and there's just a lot that we should be proud of. And there's a lot that is of exciting things that are going to happen over the next 1 to 2 years that I think we're going to be able to be even more proud of. Scalability is definitely one of them. And I guess the topic that we're talking about today is very much a part of that.
Thank you so much. Can't wait to see what you have to share on the topic. We have a few people joining the call. They may have some question. If time permits, we can take it at the end of presentation. Mm-hmm. All right. Over to you, Vitalik.
Excellent. Okay. So great. So today we're talking about the gas limit. So I guess start off with a bit of a philosophical background, right? Which is just like, why do limits have to be set on anything? I mean, I know like these arguments are probably more popular in the Bitcoin or at least parts of the some parts of the Bitcoin community than in the Ethereum community, but there is sometimes like a lot of confusion that arises about like, why do limits have to be set on anything, right? Like, why can't we just think about it as, hey, the miner is creating a block and they're selling block space, and if they're willing to sell block space and the person sending transactions is willing to buy block space, like, why not let as many of those transactions as the market is willing to accept happen? And the reason why that kind of approach does not work, right, is negative externalities. Like, basically, when a block gets included into a blockchain, it's not just the miner that creates that block that pays costs. It's also every node on the network ever in the future that's going to actually have to download and verify that block. And and that's not just mining nodes, it's also users, it's full nodes in the present, it's archive nodes in the future. It's also just anyone who benefits from the network and that benefits from it being more decentralized instead of being less decentralized. So there's this large set of actors that benefit in all sorts of subtle ways from a blockchain being decentralized or a blockchain being small, and who get harmed by a kind of every extra unit of effort that it takes to validate the chain. So in economics, like, we generally can think about this as in the intersection of the kind of demand curve and the social cost curve, where kind of the blue line is basically like, how much are people willing to pay to get transactions included, and it goes down because as you include more transactions, you include the most valuable ones first, and then after you found the most valuable ones, the ones you find after that just become less valuable than the ones before. And then the social cost covers just all of these costs that in this case arise as a result of the blockchain becoming bigger and bulkier, right? And there's good reasons to believe that this line is increasing, right? So like, if the block size increased by a factor of 10 tomorrow, like, that would not just be 10 times more pain than we have tomorrow. That would be like much more than 10 times the pain. And that's especially true in the short run, right? Because in the short run, there's a lot of risk like there's a lot of existing hardware that would break. There's a lot of things that would become much more difficult. Eventually, uncle rates would go up, and at some point, you start hitting that wall. But the point is, right, that at some point there is an intersection where, kind of from the point of view of the ecosystem as a whole, you get this level where after that point, the more transactions coming in to being accepted by the network is no longer worth it. So some important points, right, is that like this graph looks very clean and mathematically precise, but in reality, we're making very wild guesses about the positions of all of these curves, right? Like we are just sort of making a lot of guesses out of the blue. We're making there's a huge amount of uncertainty. We do roughly know the shape of the curve, but we only have a vague impression of what the curve actually looks like, right? So there's a lot of uncertainty. And even if there wasn't any uncertainty about what the curve looks like, there's no kind of hard boundary between safe and unsafe, right? Like it's not the case that there exist two worlds, you know, the safe world and the unsafe world, and we're in the safe world or we're in the unsafe world, and our job is just like coming up with a limit that's low enough to be really, really sure that we're in the safe world. Like it's not like that at all, right? There's trade-offs. There's a safe world, there's a slightly less safe world, there's a slightly less safe than that world, there's an unsafe world, and there's a very unsafe world. And even Ethereum itself has already, on many occasions, made choices to not maximize safety, right? And like we have increased the gas limit. We just added increased functionality in the first place. There's a lot of things that have been done to improve functionality and allow more things to happen for the benefit of users. And so like it is a trade-off, right? And there's and we do have to make a kind of cost-benefit analysis of some kind. And this number that we end up with, whatever the result is of the calculation, like 1.5 times more than that is probably going to be fine too. 1.5 times less than that is probably going to be fine too. I mean, obviously, and the people who benefit and the people who pay the costs are very different. But like we do need to remember like this fact, right? That it's like it's not the case that we have to choose the limit such like or whatever limit we choose, like that's a really exact number. Like it's very vague. There's a lot of kind of room for differences in opinion, and ultimately it is a guess, and ultimately it also is a choice of like what level of what types of risks the community is willing to accept. So how is the gas limit set, right? So today, the gas limit is set by miner voting. So miners can vote on the gas limit. The miner who creates a block can, in that block, vote the gas limit up or down by a factor of 1/1024. So if the gas limit today is 15 million, then they will be able to push the gas limit up or down by a factor of somewhere around like what about 14,600 and like 40 or so, something like that. And then so the gas limit can go up or down, and it's the voting basically happens because you constantly have miners voting it up or down slightly in various different directions. Sometimes you see there's a lot of disagreement, and and you can even see the gas limit is kind of fairly rough during some periods of time. And then sometimes there's a lot of agreement on a single number, and it looks extremely smooth. In practice, miners usually end up listening to the core developers, right? This is just a fact of like how this voting ecosystem has operated sociologically for the last few years. Like basic miners generally wait and see what Ethereum core developers say and think, and they generally like go based and make their votes on that basis. I think that comes from a lot of motivations. Like one of them is that miners themselves tend not to be experts in all of these subtle issues. Miners also like they are part of the Ethereum community, and they do want to see Ethereum succeed like everyone else. And core developers are some of the most experienced people in the community, and so their perspectives on this are valued. But like this is basically what happens today. Now, what are the social costs of high gas usage, right? So like here in this, I have this kind of red line that shows like there are these, vague nebulous costs that are paid by everyone in the ecosystem. Everyone in the ecosystem suffers more as blocks get bigger, but what actually are these costs, right? It's importance to be able to understand and quantify them, or at least understands them so that we can try to quantify them. So gas pays for three resources, right? So the three resources are bandwidth, so meaning bytes that have to be sent over the network, computation, so like number of milliseconds that it takes to verify a block, and storage, number of gigabytes on your hard drive that it takes up. I mean, technically, there's also a couple of other things to add, like, for example, gas pays for like how full the Bloom filter is. Though, in my opinion, the Bloom filter stuff is not going to be relevant in the long term because there's just going to be a much better second layer protocols for doing filtering of history, and people are just going to start using those. So focus on the three, right? Bandwidth, computation, and storage. And storage includes storage of state, and it also includes storage of history. Bandwidth and computation are both real-time costs. They mostly affect nodes that are running at that exact moment that the transaction was included on chain. Storage is a cumulative cost. A storage cost made now is a storage cost that has to be paid by all nodes going into the future forever, or at least for, well, if the protocol never changes, then forever. If we add state expiry and we add history expiry, then it goes down to being 1 to 2 years. But like the point is, it is a cost that goes into the future. So these are the three main costs, and we can analyze them individually, though as it turns out, there are also interaction effects between them as well. So bandwidth, right? So this is the average size of an Ethereum block. On the current average is about 60,000 bytes. And this is, again, not that big. If we compare to Bitcoin, for example, so Ethereum has, I think, something like 37 blocks for every Bitcoin block. So if you multiply 60 by 37, like you get about 2.22 million bytes. And Bitcoin blocks on average are like, I think, somewhere between 1.2 and 1.4 or something like that. The theoretical maximum size, however, is 937,000 bytes. So this is the theoretical maximum size happens in the case where the entire 15 million gas in a block is used to pay for basically just data. There are three situations in which something close to that can happen. One is that there are some applications that just legitimately consume much more data than everything else. So for example, Starks, hash-based zero knowledge proofs, they have a fairly low computation cost of verifying, but they have a very large size. And so a single Stark can often take up a few million gas, and a single Stark takes up like more size than an average Ethereum block. Number two is like if someone just wants to use the Ethereum blockchain to store a cat picture. Such things were more realistic in earlier times, but in present times, of course, storing a cat picture on Ethereum costs thousands of dollars, and so nobody does it. And then reason number three is rollups, right? Rollups are a layer 2 scaling solution that move computation off-chain and that use fancy compression tricks to move most data off-chain at the expense of more computation that also gets moved on-chain, but their bottleneck is still data that's on-chain. And so in a theoretical or projected rollup dominated ecosystem, the bulk of gas could potentially be just spent on data and blocks. So theoretical maximum 15 million divided by 16, 937,000 bytes. So this is a very naive way of trying to analyze the bandwidth problem, right? So basically, the average user has an internet band connection of 100 Mbps. Therefore, clearly the blockchain should be able to handle blocks well over 10 megabytes, right? Wrong. So here's why it's wrong, right? So naively speaking, 100 million bits per second is 12.5 million bytes per second, which is 162 million bytes every 13 seconds. But why can't we have 162 megabyte blocks? Well, here we go, right? So there's like this cascading set of reasons that stack on top of each other. So first of all, internet connections are often much slower in practice than advertised, right? Like I have been to lots of places, used lots of internet connections that promise one number, and in practice, sometimes they do deliver that number, and sometimes they totally don't deliver that number. Sometimes this is just some inexplicable property of the internet connection itself, or it's some kind of throttling, or sometimes it's because you're doing other things on that internet connection at the same time. Sometimes it's other reasons. So like, let's say you need a 5x buffer for that. Peer-to-peer network overhead. Blocks get received multiple times. I believe that the way that Ethereum nodes work now, and if I'm wrong, correct me in the comments, is that a node actually, when it receives a block, it sends out the full block immediately to a number of peers equal to the square root of its peer size, or something close to that. Now, theoretically, you could make a protocol that's more efficient, right? You could replace every single send with a probabilistic, or with a kind of check and send protocol that's like, step 1, ping, do you have this already? Step 2, reply, no. Step 3, send, and if yes, then don't bother sending. But if we actually did this, then there's like this trade-off, like having more data efficiency means that there would be more latency, and latency leads to pretty high uncle rates. Because of this, nodes end up sometimes receiving the same block multiple times. So there's a peer-to-peer overhead, mempool overhead. Nodes also end up often receiving transactions. They often end up receiving transactions multiple times. So there's a lot of overhead. And also, in case blocks arrive quickly, you need a buffer. If a node is briefly online or offline for a short period of time, or if there's a very short-term network glitch, then nodes need a buffer. So there's all these reasons why these things stack on top of each other. And if just naively, let's say we multiply like 5 times 5 times, I don't know, another 2 times another 2, that's a factor of 100, 162 megabytes divided by 100, or 1.62 megabytes. Like, there we go. I think in practice it's less pessimistic than that. Like, in practice, there are ways to optimize all of these things, but the point is that like going well above the kinds of levels that we're at now is something that's going to require more optimization, right? And optimization can be done to some degree. But it is something that, like, basically there isn't like magic room for 2 or 3 orders of magnitude for improvement here. At least if we want regular users running phone nodes to be something that remains possible. And I would argue it has to remain possible, especially because in a proof of stake context, like we definitely do not want to go even further in the direction of incentivizing everyone to just like entrust their node to a stake pool.
Can I ask a quick question?
Yes.
I'll go back to the list of
4.
I'm just curious if you have a sense of which of these are like worse and which of them don't matter as much, or if they're kind of equally problematic. Like, is there one that's more critically difficult than the other?
I think mempool overhead is probably if we want to solve that, then we can just solve that by using second layer transaction relay markets. Peer-to-peer overhead, if we want to solve that, we can reduce that at the cost of greater latency. There's multiple ways to do that. There's also fancier techniques that involve erasure coding, but I'm not sure if you wants to go that far. Let's see. You could make an argument that you can stack, or you can kind of merge your risk buffers. So you can have one risk buffer of say 5x to account for both internet being unexpectedly slow and the possibility of your node going offline, and just accept that you'll lose liveness briefly if both of those problems happen at the same time.
In my opinion, the first one is the biggest one, because realistically, we want people to be able to run Ethereum on their laptop and not have to choose between whether Ethereum works or whether Netflix works. They should be able to browse YouTube and play World of Warcraft and do whatever things you want to do on the internet, which is why you bought your 10 megabit connection. Not just run an Ethereum node 24/7 and that's it, and you buy a second internet connection so you can actually use the internet. That's not a trade-off we want users to make.
Agreed. That's a very good point, Mike. Like I think we want to be at the point where running a node is not just possible, but it's like low effort or low resource enough that people are willing to just like keep the node off or keep the node on. Because once you start thinking about like strategically turning it on and off for specific applications, that's when people get too lazy and just stop bothering entirely. Okay. So that's bandwidth, computation. So status quo, blocks take around 300 to 400 milliseconds to process. And so naively, there's about 40x room to grow, right? And like, there is this arguments that was also made historically that's like, oh, the only reason why we need a 40x buffer is because we have this problem with uncle rates because of the Poisson distribution. But in reality, if we just switch the consensus algorithm to something where blocks arrive at more constant intervals, then it becomes okay for block processing to take up like 75% of the block time instead of 3%. And then, we can just get 1.5 orders of magnitude of scalability for free. I really disagree with that argument, right? And here's the reasons why I disagree with that argument. Basically, we need safety buffers. Both, like, yes, we need the safety buffer because we have a Poisson distribution and because uncle rates go up, but also we need safety buffers for spikes of block activity. 300 to 400 milliseconds is an average. Sometimes blocks might just have more execution than average, even innocently, but even worse, there are going to be some types of execution that clients are better at, and sometimes types of execution that clients are worse at. And attackers that want to hurt the network are going to basically create blocks that are entirely full of transactions that take a maximally slow amount of time to execute. This was something that the Ethereum network was crippled by for more than a month in the 2016 Shanghai DOS attacks. Ethereum was actually very vulnerable to a milder DOS attack until recently. Basically, if you just made blocks that spammed either ext code or balance opcodes or sload over and over again, then you would be able to make blocks that take up to 80 seconds to process. And I think with current gas limits, it would even go up to 100 seconds. EIP 2929 and the gas repricing there cut that problem down by a factor of about 4. And then some improvements by the wonderful team maintaining and improving the Geth client code. I think improved that by another factor of like somewhere between 5 to 10. And so we're definitely at a, it's that like, that DOS vector is definitely like very well mitigated now, but there's always the possibility that there are other DOS vectors that we don't know about, and so we need a safety buffer for them just in case. Safety buffers for, once again, users going offline for short periods, like if my internet goes offline for 1 minute, like if, let's say, blocks took 75% of a block interval to process, then if I went offline for 1 minute, then it would take me 4 minutes to catch back up to the network, right? And like that's also a big UX loss that we don't want to see. So there's lots of other reasons for safety buffers in addition to the Poisson distribution argument, and so. Like basically, the arguments that if we just move away from a Poisson distribution, then everything is going to be better is like a little fishy. So good news. Uncle rates are no longer a big deal, actually. So uncle rates have been stable at about 5%. So these other things are still a problem. Storage. Yes.
Can I add one more thing to the computation one? So this is basically the same thing as for the bandwidth. We want regular users with regular laptops to be able to use Ethereum. And that means people with laptops often close their laptops at night, or they go on an airplane or a train and their laptops don't have internet for a while. And we want those people to be able to catch back up. Like, we don't want it to be like you sync Ethereum and then if you ever turn your computer off, you can't sync again. Like, and we also don't want it to be if you turn your computer off for 8 hours a night, it takes you 16 hours before you're caught up. So you can't do any transactions until the evening of the next day. And so these things are like, having a big buffer lets us let regular users do regular real life things without having to think about operating an Ethereum client as like a kind of like you're running a company. Like this is just like, oh, it's just like BitTorrent, you know, it's just sitting on your laptop or whatever, it's running in the background when your laptop's on, when your laptop's off, it's not running. And when you want to use it, it's there. And that's what we kind of want Ethereum to be long term. At least that's what I want Ethereum to be long term.
No, I definitely want this as well. And I think again, there's definitely arguments that, you know, status quo Ethereum makes it difficult to run your node. And I think, you know, we have made compromises just because the alternative would be like half of Ethereum activity not being able to exist at all. And that like there's huge downsides to people. Like there's no point in a system that's decentralized if people can't use it, basically. But in the like, we have all of these amazing scaling technologies coming, including fancy roll-up sharding type stuff, but also including more kind of nuts and boltsy, you know, factor of 2 improvements that stack on top of each other. And I think it would be nice if we could like basically share the gains that we get from those improvements between increasing the gas limit and actually making Ethereum nodes easier to use than they were in the past.
Yeah, that's fine.
Okay, so storage. So storage is, thank you everyone for reminding me about time, because storage is important. It's because it is the specific thing that core developers point out is believe is actually the dominant blocker at the moment. So there's 2 main types of storage. There's state, which is 30 to 100 gigabytes, depending on what format you store it in. So the state in a highly compressed and like zipped and form is about 30, but then if you want to add just like an easily accessible address to the data map, then you know, you have to add another like 10 gigabytes, 15 gigabytes if you want to add the Patricia tree. So you can recompute state roots quickly. You have to add like another 40 gigabytes. If you want to add some other some indices, you have to add another 5 gigabytes. So it goes up to 100 if you add everything. I think it's around 30 for like a bare bones version. And then history is about 150 gigabytes. Storage requires fast access. So because you know, a read of storage is a 1900 gas, and so potentially up to almost 800 of them can happen inside of one block. Or actually, so I guess oh right, yeah, it is 1900 if it's inside of an access list now. So storage cannot be stored on an HDD. Storage cannot be sharded as easily. Like history can be sharded, right? Because you can just say, well, nodes don't have to store it, and instead, like say the Portal network stores history instead. And if you want history, just go ask the Portal network. Much more disk wear and tear for the storage. So the reason why this all matters is that a lot of computers do have these kind of hybrid setups where, you know, you got an SSD and then you got a bigger HDD. And in addition to both of these things, sync times. So once again, the Geth team has done, and other client developer teams like, you know, Nethermind and others, like they've all been doing amazing work making sync more efficient. Last time I tried syncing Geth from scratch, like which was soon after they introduced snap sync. It was 18 hours for me to do a snap sync. So this is another cost, right? That's just like the cost of spinning up a node. And the time needed to spin up a node is not just a UX issue that contributes to decentralization. It's also a security issue, right? Because if some kind of glitch happens that causes nodes to stop working, then often the fix to the glitch is to just like spin up a node from the beginning. And if spinning up a node takes 18 hours, then that's one thing. But if it takes like 180 hours, then that's a totally different thing. So sync time's another very important thing. I think they've been hovering close to the kind of like 12 hours to 1 day level for about a couple of years, and basically growing state size is being roughly counterbalanced by improvements in clients. But eventually improvements in clients are going to hit a limit unless we implement things like state expiry that we'll talk about. interaction effects. So the cost of storage read and write goes up with is proportional to, actually, that's a bit of a mistake. It's technically bad math because it's not linear. Cost of storage read write becomes more expensive as the size of the state increases. There's two reasons for this. One is just the way the databases work. In any database, they're all tree structured in some way or another. And so the number of disk reads is proportional to the logarithm of the number of steps you have to walk down the tree before you get to the cache that's in RAM. And so it's about proportional to the log of state size divided by RAM cache size. So if the state size is 64 gigabytes, and let's say the RAM cache size is 4, then that number is 16. If the state size increases by a factor of 4, then that ratio increases to 64, and so the logarithm goes up from 4 to 6. And so that's another factor of 1.5 to execution time on top of the factor of 4 to execution time. And then reason 2, disks become slower as disks come closer to being full. There's more kind of compaction processes, there's like more wear and tear issues, there's more of other things. So conclusion is that a gas limit rise of a factor of 4 may well correspond to an increase of a factor of 6 or potentially even more in block processing time. So will increasing the gas limit to 30 million break Ethereum? No, right? But it will significantly increase risks. It will increase centralization. It will increase denial of service risks that affects like both users and applications. It will increase the risk that something in the network just breaks. It will increase sync times. It will increase hard drive requirements. It will increase a lot of things. And so, at the end of the day, there definitely is this kind of there are trade-offs involved here. I would argue that the case for increasing the gas limit drastically is even weaker now than it was like 2 months ago, because 2 months ago, people were kind of screaming to get in the door to send more Ethereum transactions and were even willing to pay 500,000 GUI for the privilege. But now the markets have actually calmed down a bit. But at the there is a trade-off, and there's there's definitely more work that can be done to concretely measure these things, right? So it's do we want to have, say, a test net and say, on our test nets, we're just going to have 80 million gas limits? That might actually be a good idea. It might actually be a good idea to just increase the gas limit on our test nets from 15 or from whatever it is now to some high number like 80, just so we can have an environment where people see what it's what that's actually like for a node operator. And maybe that'll give everyone on all sides more information to feel comfortable. So reducing uncertainty will definitely help us get closer to a value that's actually optimal. Another thing that will help us get to a value that's optimal is mitigations to the problems of increased gas usage. One of them is Verkle trees and statelessness. So if we have nodes can be stateless, then sync times for those nodes stop being an issue, and hard drive space for those nodes stops being an issue. But Verkle trees and statelessness are also not a panacea, right? Because there are things that stateless nodes cannot easily do. Like they cannot easily do high-speed analytics. They cannot easily kind of just grab data about the state and history. So they're okay if you want to verify, but if you want to do more things, you might still need a state carrying node. State expiry. This is this concept that we reorganize the state so that objects that have not been touched within the last 1 or 2 years go into a separate tree. And if they're in a separate tree, then even state carrying nodes do not store them anymore. And if you as a user want to use that object again, then you personally have to go find a Merkle proof for it and provide that Merkle proof as part of the transaction. Peer-to-peer networking improvements, constantly happening, but it can happen more. Also, nodes can stop downloading and storing history, let's say older than 1 year. So I think I would argue this will actually happen automatically to some extent as a result of the merge, right? Because as a result of the merge, like potentially we'll have nodes that just stop downloading the proof of work chain that's before the merge. And so we'll have a bit of a reset to zero moment, which will be nice, but it would be nice to make that rolling, right? It would be nice to make it rolling so that, nodes don't have to download all and check all of those blocks from zero unless they really want to be archive nodes. And there are legitimate reasons for applications to want to look at deep history, but like if they want to do that, they should not be using the base protocol to do it. They should be using separate protocols that have like simple forms of sharding, that have simple forms of like torrent or like DHT type logic. And the Portal network, once again, like Piper Merriam, Jacob Carver, and those people have been doing excellent work pushing this forward. So that's also another mitigation. So, if we have statelessness and state expiry, then I think my impression from talking to people is that a lot of people will be totally fine with a gas limit increase of like even a factor of 2. If we have all of these things, and then we'll again could potentially go even more, but then we may also want to just say, well, no, the gas limit only goes up by a little bit. And we're going to use all like the extra mileage that we get from this to actually go back to an Ethereum where running nodes is like extremely accessible for people the same way that it was in 2015 or 2016. Now, one other thing is that if we set our, if we decide we're going to do state expiry, then theoretically we can increase the gas limit like potentially a few months or like half a year before we actually start doing, or before state expiry actually comes out, because we know that like if we have certainty that we'll actually be able to start expiring state like as soon as the increased gas limit becomes a problem. But I think for people to feel comfortable doing that, like we probably at the very least have to have the Verkle tree EIP fully figured out and actually like on mainnet, and probably like know what we're going to do for address space extension as well, and just have the state expiry de-risked and make sure developers are comfortable with the full consequences. So I think we're far from the points where people feel like state expiry is something that they've kind of fully grappled with their heads around. I think people are very supportive of the concept in theory, but there isn't like certainty that it can happen within any specific time frame. And the sooner we get to that point, the better. So that's the that's the presentation. Also happy to answer questions.
Thank you so much for the presentation. Yeah, I know we are running short on time, but still, whatever time we have got, I'd like to open the floor for anyone to add any question, comment, or concern that you have.
Can I push back a bit on this? Like I was holding until the end
Sure.
of the presentation with the questions on this. But Vitalik, so everyone, I'm Uri from Bloxroute and from Eagle, the Ethereum gas limit project.
Yes.
Vitalik, at the beginning, you start by saying that there's no safe or unsafe, right? This is a trade-off. And so I want to push back against like at least the laptops argument. There is a question, who should be deciding on the gas limit? And what is, I think it's a community. But there's a question, well, you have this giant DeFi environment where you have a lot of actors who participate and they're running their own IT and et cetera, and they're running their own nodes. Do we want, and maybe the answer is yes, but do we want nodes to run on laptops? Or is it okay if they can only run on PCs? Like, it's like if you're a dev, it's great if you're a participant. And I don't know the answer, but the question is, who should decide this? Who should decide whether it should be able to run on a laptop where you always get on and off, or as Ethereum matures and you have a lot of actors with much higher like IT budgets, is it okay that there's enough, whatever enough is, there's a lot of private nodes or individual nodes for everyone. So like, do we want it, or maybe who should decide this?
Yeah, sure. Again, I think like I mean, so like my personal view on the object level question is that there's like 50 Ethereum killers out there that are willing to concentrate on the 500 nodes is enough for everyone niche, and blockchains that are like committed to node decentralization. The major ones are just basically Bitcoin and Ethereum, and so that's like I personally find. So like, this is why I personally find it more like interesting to basically focus on trying to maintain that property. But in terms of the who should decide question, like I think it's like the gas limit is not the only issue on which that kind of conflict exists, right? Like to just give other examples, like there's questions of proof of work versus proof of stake. There's questions of backwards compatibility versus scalability. So like, for example, state expiry, which I am a strong proponent of, and many other people here are strong proponents of, comes with the downside that it'll probably require most major application developers to rewrite their contracts within a decade. There's, using Kate commitments for data availability sampling increases our vulnerability to fancy moon math cryptography. Like there's these kinds of trade-offs everywhere. And so coming up with better ways of solving them is just part of this general, governance problem. And the governance problem is hard, right? And I think there's I guess I personally am of the opinion that governance, especially governance problems that are a matter of trade-offs between things that are that hard to measure, probably can't be solved easily just by kind of introducing magic gadgets. So that's one thing, right? Like, so, and then the other, like, I think it's, 80% discussion and 20% mechanism, basically. And then the other thing is that for a lot of these things, like whatever the decision is, people would want kind of just predictability of that decision and have that decision be something that's like known ahead of time as much as possible, right? Because like, if you build, let's say, a wallet that is designed around the assumption that you're going to be able to verify everything locally, and you start doing your marketing around the idea that like, hey, my wallet is amazing because it's decentralized, and then the community decides to bump up the gas limit by a factor of 4 within a month, and suddenly your entire marketing pitch has basically become a lie for reasons that are not your fault, right? So like for reasons like that, I also think kind of predictability of the values of at least what values or what things the governance is trying to maintain is something that's very useful too.
But isn't it the current state much worse? Like you mentioned earlier, like, okay, gas limit is decided by the miners, which in reality isn't true. In reality, it's decided by the mining pools. And 40% of the
that's not where I thought you were going. But I thought you were going that in reality it's decided by the core developers.
No, so I would argue that it isn't. Like I would argue that when mining pools, like 40% don't participate, like top 3, top 4, when they increase from 8 million to 10 million, much higher jump, like a really big, like 25%. I remember you tweeting saying, well, Spark Pool told me they're thinking of doing it. I told them I think it's not the greatest idea, but like I understand that they're doing it. When they increased it again from 10 million to 12.5 million, Peter from GIF was yelling at Twitter saying like they shouldn't be doing it, but they did it. So I would argue that A, they don't listen to core devs, and B, the current changes are much more drastic. They out of the blue, there's no predictability. Out of the blue, they increase it by a lot. Why is the current status quo better?
I mean, a factor of 1.2 is not a lot, but I think I would say that miners, like well, okay, they don't implement the exact same thing as core developers' preferences, but I do think that they listen to core developers. I do think that like if core developers were to give a hard no to a number, then that number would not become reality, right? Like even another example of this is like the increase from 12.5 to 15, like that, patiently waited until a week after Berlin to happen. And then the other thing, of course, is that if miners start like pushing the gas limit up to 100 million or down to 1 million or whatever, and that's incompatible with the community's objectives, then like I think realistically, like they know that if they started doing that, then the next hard fork would just hard code it, right? And I think the ecosystem actually like benefits from being able to set the gas, have miners set the gas limit flexibly. Like for example, it allowed a very effective defensive response to the Shanghai DOS attacks. But like that's different from a kind of an enshrined architecture where they have the power and they have the legitimacy to use the power in whatever way they want.
I'm not sure I understood the last piece, because currently they do, or like unless
no,
they do something drastic, which appears
right.
to be an attack. But like we agree on that.
Mm-hmm. Yeah.
Okay.
Okay.
But and last thing, because I feel I'm hogging the conversation, but is this a technical question or a question of values? Like, because I disagree with a bit regarding the technicality, but at the general level, I agree with you. But is the gas limit really, at the end of the day, you need technical people to translate that into a budget, how costly it is to run a node, and then it's a question of values, how decentralized you want nodes to be compared to how decentralized users, like how cheap it is to participate. So is it a question, is it a technical question, or a question of the values of the community? Or what is it both?
I think, well, keep in mind, it's not just decentralization in a vague nebulous sense. It's also kind of concrete security. Like to give one example of this, as I remember when Starkware did their tests, when they flooded the network with like half megabyte blocks for the first time after the call data gas cost reduction, that did actually end up like, I think, kicking a couple of bootstrap nodes off the network, right? And like that was, I think, because of issues that should have been, and I believe have since been resolved. But like there are also security issues. There's also risk of unknown unknowns, and there's risk of like things concretely breaking as well, right? So, but at the same time, like this is also a values question, right? Because like it is very possible to have a community whose value system says that like, yes, we are totally fine with having 3 or 4 like 12-hour outages every year and kind of needing to centrally coordinate to bring things back together again. So like decentralization is a value and security is a value. There's definitely a point that like we need to carefully distinguish between technical judgments made by technical experts versus technical experts kind of using technical judgments to sneak in their own opinions on values where like on that question they really don't have or shouldn't have more of a say than anyone else. But well, so I guess like that is a valid point, right? And I'm not like defending a kind of core dev, like a structure where core devs have legitimacy to set the gas limit to whatever they want either. I think my only real opinion is that like these questions are complicated, and like the path that we've taken so far is basically status quo, but or maintain the status quo, but if there's a lot of pressure in one direction and there's no significant pressure against, then the gas limit changes in that direction. And so like it is a very de facto multi-stakeholder model, and I don't know, it seems like it's been working all right.
I'm holding myself from hogging the conversation.
Okay. No, this is a conversation that needs to happen. I mean, you may want to also just like publish a screed on Mitigations. I mean, I personally think like we actually need to have just more people publishing screeds. It's like it would be nice to have these ideas just discussed in long form.
Well, I was polite for like 10 seconds, allowing other people to talk before I talk again.
No
so-
problem. I enjoy your chats. Thank you.
I appreciate that. So I think generally on the technical side, I agree with you, but I go back to the question of who decide the gas limit. And so we're talking about like ETH2 validators and the merge coming up. I'm running my own ETH2 validator. And then now the decision, what to set the gas limit to, is mine. I have to configure it. And I have no idea. I have no, like, except for Peter saying, being against any single increase in the past, like, I don't know, 2 years on one hand, and the Oregon team being in favor of increasing the gas limit, I have no idea what core devs think, and I'm not sure even core devs have the answer. Like, I want to know what the community thinks, I think. And so how do you think about setting the gas limit, and how that should be done? If we don't want it, as you mentioned, you said, I don't want just core devs to decide it.
Yeah. Okay.
Then how do we go about it?
Right. So I think like for me, my like one ideal or like one example process would be like, I think step one is more information gathering. Like one example of information gathering, I would love to just even hear, even offline, like what people think of this idea of like, let's increase the gas limit on Robson or Gurley to 40 million. Right, like one of those test nets, just so that we have one test environment where the chain is considerably bulkier and heavier than it is today, and so it's like it's not scary. It's like it's a much more concrete thing of like what that world looks like. And then, you know, if we have that information, then like I think information gathering is step one. Step two is like. I mean, we've had like various kinds of polling, like we've had various ways of like of just getting community sentiment for things. So I think just use those existing techniques, like the same sort of stuff that ended up deciding, you know, EIP 1559, the issuance reductions, all of these various sometimes a controversial trade-offs that have been made, and go from there. I mean, I don't think we necessarily even needs to have the roadmap planned out. I think if we wants to make a decision that like the question, like this is a question that's very important to Ethereum, and we should like actually like put a lot of effort on just like this data gathering and like making the world of Ethereum with a 3x higher gas limit more concrete, just so that it's less of an abstract and more of a very specific thing of like deciding whether or not that's a good world to go into. I mean, I'm definitely in favor of that.
I think that there's also like an element of, you know, there's this illusion, there's this vision that miners aren't listening to the core devs, but I think they actually are to an extent. It's just that there's not good communication channels open. Like back in 2016, when the Shanghai attacks happened, we literally were able to bump the gas limit down to something like 2 million in like 6 hours.
Like 1.5 million in much less than 6 hours. Yeah, no, that was amazing.
Yeah, it was really cool coordination, but now we don't have those bridges and those communication channels. So having that set back up again with some of the major mining pools, I think would be important. And we have some people who can probably do that. So yeah, that would be the step I'd take if I was king.
Yeah, that's sounds good.
But Hudson, just on that, we like Blockhead, we work with the mining pools. We work with all the top 20, and we asked mining pools like, how do you decide on the gas? Like, do you want to increase it? Do you want to decrease it? And many of them weren't even aware that they control the gas limit. I think you're missing the point that mining pools in general don't affect the gas.
Not for the majority.
That sounds unlikely. That sounds unlikely to be true, because otherwise, like, how is it possible for the gas limit to go up from 12.5 to 15 million a week after Berlin?
I think that's true. I think it's true, but the problem is you're talking to a lot of different mining pools, and what really matters is the fact that like how much 70% is within 5 pools, and they all know how to change it.
Right. Yes. Okay.
So we've all.
By the way, I do have to disappear for this HackFS thing, so thank you very much.
I really appreciate Vitalik taking out time to join us and provide great explanation. Thank to Micah, James, Hudson for adding relevant information, and many thanks to Uri Klarman from Blockstrout Labs for joining and sharing his questions and concerns. I really hope you may have received answers to some of the questions that you were looking for. There are some questions related to governance, which I think will not be answered in this call, but we'll try to organize a bigger community call or maybe a kind of AMA session with relevant people. Well, I hope the recording of this talk helps with the understanding of the concept and would increase support for important decisions like setting the limit. On this note, for our YouTube viewers, thanks for watching. In the description section, you will find different resources on the topic and the Twitter handle of the guest to follow. If you liked today's episode, hit the like button and don't forget to share it with people of similar interest. If you still have an unanswered question, leave it as a comment. I read all the comments. Also, if you have missed watching the episode, A Brief History of Ethereum's Future with Ben Edgington, please check it out at PEEPanEIP playlist at Ethereum Cat Hunters YouTube. As usual, I'd love to hear feedback and improvement suggestions. Let us know in the comment below which proposal or topic would you like to see in the upcoming episodes. We have more interesting talk coming your way, so stay tuned, keep watching, and keep sharing your love with Ethereum Cat Herders. Talk to you soon in the next episode. Thank you everyone for joining us today.